Chemical Characteristics of Chlorophyll by Connor Davenport. The objective. After the presentation, the audience will be able to explain the general classification and chemical properties of chlorophyll. This is the general Lewis diagram of chlorophyll. You can see the various structures. We'll be going more into that in a moment. This is a general bond line structure, two different representations. The one on the left is from the internet, and the one from the right I generated on a program that downloaded from the internet. There are various hybridization states expressed by each atom in the molecule. If you'll notice at the bottom left-hand side of the image, a large carbon chain has been removed just for convenience sake. It has no significance here. If you were to do this same procedure on the chain, however, you would get almost completely sp3 hybridization. The remainder of the molecule is nearly completely sp2. And the few exceptions can be found immediately in the middle with the magnesium ion, as well as the peripheral carbons, hydrogen, such as the carboxylic acids and the ketone. Again, we'll discuss those later on. Bond types. There are several different kinds of bond types going on. I can elaborate with the photo, which will help clear things up. But as I mentioned, because of the many sp2 hybrid orbitals, the overall molecular geometry is planar. And this has significance within the cell when closely packed together and receiving energy between each other and from the sun. Also having to do with the molecular geometry. Since it is planar, there is no axis for the electronegative charges to pull in any other direction except on the same plane as the molecule itself. So the dipole moments only lie on the same plane as the molecule. However, the exception to that is the long chain of carbons that will result, or that will be skewing the dipole moment depending on which direction they are oriented. And that's because of the oxygens on the bottom side of the molecule. These oxygens dramatically influence the dipole moments of chlorophyll and actually aid in providing really strong hydrogen bonds between other molecules. Off the same program, I have labeled each of the functional groups. You have a ketone starting at the top, and right next to it you have a carboxylic acid. Immediately adjacent to that is an ester linkage, which is created from another carboxylic acid becoming esterified or dehydrated. Sorry. Down the carbon chain from there is an alkene. And this signals the beginning of this long chain of carbons that was brought up earlier that is called a phytol. Turning back to the main structure, there is an alkene indicated at the very bottom of the planar structure. And then the bulk of the structure itself, while containing many double bonds, is actually an entire conjugate system, which will be addressed in the following slides. But its functional name is as a porphin ring, or more specifically a tetradentate cleating ligand. And these ligands are essentially the key to how autotrophic organisms create energy from light. Resonance structure is fairly more complex than was anticipated. In this structure, however, it has been simplified into a single hybrid resonance structure. Also indicated on the structure are the partial positive charges and the unpaired electrons on the superior methyl and the furthest ketone. As was mentioned, you see the positive charges and the unpaired electrons off of the ketone and the ethyl group. The chlorophyll actually acts as an electron donor in order to preserve the photoelectric energy as chemical energy. So we would consider this a Bronsted base and a Lewis base as well, as an electron donor and as a proton acceptor. And this concludes my presentation. I hope you're capable of setting out and fulfilling what my single objective was. Tell me a little more about the molecular model of chlorophyll. Thank you very much for listening, and have a wonderful day.